Today we are going to study new section 3.2, and this is called the second derivative test. So let me remind you that last time in section 3.1 we discussed the first derivative test, and basically it says that if your derivative is positive, then your function is increasing. If your derivative is negative, then your function is decreasing. If the derivative is zero, probably you have local minimum maximum, but you should check it, because as we discussed, in situation like y equals x cubed, the derivative at point 0 is 0, but this is not a local minimum or maximum. But still it says that the slope of the tangent line is 0, that's for sure. And also we discussed how to find if it's local minimum or maximum. That basically depends on where your function was increasing and then started to decrease, or opposite. And in one case it's local minimum, in other cases it's local maximum, and we used the x line where we put it the zeros of the derivative and then determine the sign of the derivative, and that gives us the information about local minimum maximum and about increasing decreasing intervals as well. And also we discussed that sometimes you have the point where the derivative is not defined, as in this example, x to the power 2/3, and basically that's because either your derivative behaves bad, it goes to infinity, or it's not defined at all, because you have sharp peak, like on this picture, and it's not very smooth at this point. And the point that you should also check these points if you're interested in a local minimum or maximum. And also we discussed that there is the definition of the global minimum and maximum, and which is sometimes called absolute minimum maximum, and comparing to the local minimum or relative minimum or maximum. So you have, this is, by the way, it's important. I will say a few words at the beginning of the new section, just to recall, because it's important for the quiz that I created on this week. So I'll say a few words about that slightly later. And also we discussed that, again, if the derivative is 0, then it doesn't guarantee you that x0 is local minimum maximum. And at the last minutes, we discussed how to use the first derivative to graph some functions, and we discussed algorithm how to do that. And just one example, but at the end of this example, I noticed that even if you know that, okay, let me go to the new thing. So why the information that your function is increasing and decreasing is important, because suppose you have 2 points, you calculated it somehow, that your function, say at point x0, has value f of x0, and say at point x1, your function has some value f of x1. Without information that your function is decreasing or on the interval x0, x1, you cannot connect them in a simple way like that, because your function can behave very ridiculous like this and comes to that point x1. But if you know that your function is decreasing on the interval x0, x1, you already can connect it like that, in that way. What is left, and that's what we discussed at the end of the last class, that even if you know that your function is decreasing, you still have two ways to connect 2 points. Either you connect it, like that, or you connect it like that. In both cases, your function is decreasing. X naught, f of x naught, x1, f of x1. But you cannot choose which ways is correct. And to determine that, you should study second derivative, and that's what we will do in this chapter. But let me make a remark about global minimum and local minimum maximum. So local minimum or maximum. So suppose you have a function which is defined on the interval, say, AB, and you're looking for the global maximum. Then what you should check, so let's draw some graph that looks like like that. Here's your A and here's your B. Then what you should check, again, you should check the critical points where the derivative is 0 or it's not defined, and that gives you the local minimum or maximum. So here, this point and this point, or it can be just a saddle point, like an example of x cube. But still, that's what you should check. Is it minimum or maximum? And you should check it using that the sign of the derivative is changed at this point. That's what we did last time. But this gives you all only local minimum maximum. While if you are looking for the global, what you also should check, you should find the value at that point. So say it's x naught, and this is your x1. You should check the value. So this is your f of x naught. This is your f of x1. But also you should check the values on the endpoints, f of a and f of b. Because again, when you're interested in the global, you should consider the whole interval, not just the local neighborhood of x naught. If you're looking just at the local, at the small neighborhood around x naught, then indeed x naught will be the only maximum on that interval. But if you consider bigger interval like AB on this picture, then as you can see, the global maximum will be not here, but rather here at point B. So in this case, f of B is local or by local, it's a global maximum. So what I want to say that if you have some interval, then you should not only check the critical points, but also check the endpoints. And because they can be global minimum or maximum. And the same, you should check, compare f of a with f of x1. Because on this picture, it looks like that f of x1 is less than f of a. That means that f of x1 is local minimum, but it's also a global minimum. So to summarize, again, you should check the endpoints as well. Okay, this is what I wanted to say about the maybe I should put remark before the section 3.2, but maybe I'll fix it. But nevertheless, let's speak about the second derivative test, and let's think a little bit. So suppose we have a function f of x. Then we, of course, can, if our function is differentiable, we can calculate f prime of x. And we know that f prime decodes the decreasing and increasing intervals. But what if we consider f prime as just a function, and then we can calculate second derivative and look at the second derivative. And then let's think what this information will give us. So by the definition, second derivative is the derivative of the first derivative, right? So that means if we know that second derivative is positive, by the same reason that we discussed for the first derivative, we will get that f prime is increasing. And the same story with if the second derivative is negative, then f prime is decreasing. But we remember that f prime at some point gives me the slope of the tangent line. So in other words, I can say that the slope of the tangent line is increasing. Or in this case, the slope of the tangent line is decreasing. And let's see on the picture what happens. So suppose I don't know how the graph of my function looks like, but I know that for some reason on the interval a, b, say, I know that suppose that the second derivative is positive on interval a, b. And say I know how to calculate this first derivative. And so I start with, say, slope at point A, and it looks like this. This is the slope of the tangent line at point A. Then, since the second derivative is positive, the slope of the tangent line should increase. So here it was negative. It means that it becomes more like this at this point. And then it should become horizontal, say, at point here, at this point. But then it should continue increasing. The slope is increasing. And it becomes like that, and then it becomes like that. Again, how to find the values of the slope depends on your function, of course. But the point is that you see what happens with the tangent lines. So again, recall that this slope is negative, so say k is -3, while this k is equal to 0. This is slope. So that's why if k is, say, nice. Okay, let me put it here. So if k is, say, -2, then it will be like this. K equals 0 like that, k equals, say, 2, it will look like this. And k equals, say, 5 will look like this. So it's indeed increasing. And if you try to connect these points like that, you will see that your function is above your tangent line. So your function is above the tangent line. While if I repeat the same thing with so again, how to plot if you know the tangent line. So you should plot like that. So it's something that is a tangent to this, and then try to connect it smoothly. This is the way you create a graph. But again, it's not the precise way to graph. In order to do better, you should study the first derivative test, find local minimum maximum, but as draft, this is fine. Okay, this is mine. But what if I have, say, if I know that second derivative is negative on my interval AB, then I should go on the other way around. Other way around. So that means that the tangent line, the slope of the tangent line, is decreasing. So if I started with some positive slope, say something like k equals -3, then it should become more horizontal. Then at some point, maybe it will become horizontal, and then in some way it starts to be negative, and then very negative like that, and so on. And again, if you try to plot the graph using the tangent lines, it will look like this. And the conclusion is that the graph is below the tangent lines. That's what the textbook says. I think I slightly discuss it in my manner, but I think if you start with so they kind of say that if you try to plot the graph with positive derivative, second derivative, then you'll get that the function is above the tangent line. But why? And in some sense, I try to make an explanation for that. Okay. What I wanted to say that the first case, when your second derivative is positive, let's make it as a definition. So suppose you have f of x and f prime of x are differentiable, and consider the interval well, say AB, then the function, then the graph is called is concave up. The graph of f of x is concave up. Again, up means that the tangent, your graph is what I want to say. The graph is above the tangent line. That's why it's called up. If f prime of x is positive, so the graph looks like this. While the graph of f of x is concave down, if the second derivative is again down because it's below the tangent lines. That's how you can remember that. If second derivative is negative. And the point x where f double prime of x is equal to 0 is called inflection point. So why it's important point? Because at this point you'll probably have that your concavity is changed. So something like that. You had the function that was like this. Okay, I will discuss it in the examples. The most trivial examples are the function y equals x squared. That's how you can remember when it's concave up, what is concave up and what is concave down. Because if you calculate the second derivative, so first derivative gives me 2x and second derivative gives me just 2, which is positive. And indeed, this graph looks like the head up, right? So that is called concave up. And this trivial example when it's concave down, it's minus x squared, because if you calculate the second derivative, it will be minus 2, which is less than 0. And indeed, it will look like this, concave down. Should go through 0. So these are examples of the concave up and down. And what about the inflection point? Let's consider our also favorite example, x cubed. If you calculate second derivative, you will get what? Okay, if you calculate it once, you will get this, and then it will be 6x. And so you see that second derivative is negative for x less than 0, is equal to 0 for x equals 0, and positive for x greater than 0. And let's draw the graph, the corresponding graph. And that's what you see on the graph, because before, when x is less than 0, then because it's concave down, my derivative is negative, it should look like this stuff. But after the 0, when x is greater than 0, it should behave like concave up. That means that it should look like this. And here's my inflection point. So at the inflection point in this example, my concavity was changed. It was concave down, and then it becomes concave up. So at the how to say, it's similar to the situation where we have first derivative was positive and then it becomes negative, then we probably have local minimum maximum. But again, this is probably because of the example x cubed. It doesn't guarantee, but you should check this point as the point where your concavity was changed. And this is counterexample, y equals x to the power 4. So a lot of examples. So first example was concave up, second example was concave down, third example was x cubed, where you have concave up and concave down, and inflection point, x equals 0. And this example, y equals x to the power 4, will give me what? Y prime is x to the power x 4x cubed, which is 12x squared. And so second derivative will be 0 at x equals 0. But the point is that if you graph this function, it will look like this. So your function will still have concave up on the whole real line. Even you have an inflection point. Oh, I made a mistake, pardon. Where not second derivative is 0, but I apologize, but where concavity changes. Concavity changes. I apologize. That's why I'm confusing in some sense. Concavity. Changes. So in this case, concavity indeed changed, right? It was concave down, and then it becomes concave up after 0. So x naught, x equals 0 is the inflection point. While here, it was concave up before 0, and it continued to be concave up after the 0. Concave. So that means that x equals 0, even it's the 0 of the second derivative, it's not the inflection point. So in other words, like summarize it, if how to say that, okay, and one more maybe thing that also, as we have seen with first derivative, second derivative at some point can be not defined. And how to say that? Not a banner. And now the summary is that if at point x equals x naught, if x equals x naught is the inflection point in point, then either second derivative at point x naught is 0, either second derivative at this point is not defined. But again, this example other direction is not true in general. So what does it mean? It means that if second derivative, say at x naught, is 0, in general, doesn't give you that x naught is the inflection point. Yes, see example y equals x to the power of 4, right? So we found that at x equals 0, our second derivative is 0, but 0 is not the inflection point. So it's only one way. If you know that some point is inflection, then necessarily the second derivative is either 0, either not defined, but not other way around. Okay, questions about the definition and examples. Okay, so far I don't see any questions. Okay, so why second derivative is so important? So first of all, we'll discuss how it helps with curve sketching, but before that, let's discuss the second derivative test. Okay. Theorem, the second derivative test. And second derivative test says the following. Suppose you know that at some point the first derivative of your function is 0. Then if second derivative at this point is positive, then f of c is minimum value. If it's negative, then f of c is maximum value. Again, in this case, it's local. And third case, if for some reason you calculated the second derivative and it appears to be 0, then you don't know. That means that it can be, still can be local minimum or local maximum, or neither of them. So you need to investigate it differently. So again, we remember how to determine if the point is local minimum maximum. Let me recall it. If you put the zeros of your first derivative on the line x, say x0 and x1, and then you calculated that here the derivative is positive, here the derivative is negative, say, and this here the derivative is still negative, for example. It depends on the function, of course, but suppose we have such such situation, then this means that function was increasing, then it was decreasing, and then it continued to decrease after x1. So that means that x0 is local maximum by the common sense, right? Because it was increasing, then it starts to decrease. And x1 is unfortunately nothing. Not minimum or maximum. So again, in order to determine if the point is local minimum maximum, we should not only calculate the zeros of the derivative, but also should look at the sign of the first derivative. And now the theorem says that you don't need to do such complicated stuff. Instead of that, you just need to calculate second derivative and find the sign of the second derivative at that point, and that's it. If you're lucky, if you're in first or second situation. But if you're in the third situation, when the second derivative is 0, you need to do this procedure, in fact, unfortunately. So let's calculate example number 2. From the textbook, I keep the enumeration. Okay, yeah. Okay, example number 2, y equals x cubed minus 3x. So if we calculate the derivative, that will be 3x squared minus 3. Okay, what I wanted to say. Okay, maybe later. And so if we're looking for the zeros of our derivative, we'll get 3x squared minus 3 is equal to 0. Or 3 times x squared minus 1 is equal to 0. And that gives me that x squared is equal to 1. And that gives me x equals plus minus 1. And before we should put it on the line, consider the sign of the derivative and so on. But now I will calculate the second derivative. And the point is that my second derivative is, my first derivative is 3x squared minus 3. So second derivative will be just 6x. And so y prime at the point, say, x equals 1, will be 6, which is positive. That means that x equals 1 by the second derivative test. I'm in the first situation, second derivative is positive, while first derivative is 0, is the local minimum. While second derivative at point minus 1 will be minus 6, which is negative. That means that x equals minus 1 is the local maximum. Of course, we'll obtain the same result with our previous algorithm. So if I put minus 1 and 1 here and calculate, so my first derivative is compare with the old right? My first derivative is 3 if I factorize it, x minus 1, x plus 1. So if I choose the test point here, say minus 2, then y prime at point minus 2 will be 3 times minus 3 times what? Minus 1, which is positive. So here my function is increasing, while here I will choose test point 0. Y prime at point 0 will be 3 times minus 1 times 1, which is negative. So here it was decreasing on the whole interval. And for this interval, I will choose, say, 2. Y prime at point 2 will be 3 times 2 minus 1 times 2 plus 1, which is, of course, positive. So here my function is increasing. And again, from this picture, we still can determine that it's local maximum, while this one was local minimum. But instead of doing this, I could just calculate the second derivative. But again, let me repeat that you still need this algorithm because sometimes you have third case when the second derivative is 0. And this is exactly the case when y equals x to the power 4. First derivative gives you 4x cubed, and second derivative, and so y prime equals 0 gives you that x equals 0. While the second derivative is 12x squared, and at point 0, it is still 0. So in this case, second derivative test doesn't work, doesn't give you information. It works, but says that you should check it somehow in a different way. Give you the answer. All right, your first derivative is 0, and second derivative is 0 as well. And in this case, you need to do the old algorithm. So here's your x, here's your 0, and your y prime is 4x cubed. And so if I choose -1 here, I'll get -4. So its derivative is negative, so the function is decreasing. Well, if I choose test point 1, my function will increase. So that means that this point is local minimum. And it's indeed true because we have seen the graph of this function. That looks like x squared. Okay. Okay. And why it is so? Basically, I have not proved the theorem, the second derivative test, but why it should be true? Because kind of proof of the theorem. Because suppose you know that f prime point C is equal to 0. So locally, that means that your tangent line is horizontal, right? So you have somewhere the tangent line is horizontal. This is your, say, point C. This is your x, and somewhere is your y. Doesn't really matter. But then, suppose you know that f double prime at this point is positive. But that means, as we discussed at the beginning, that if my second derivative is positive, then my graph is above the tangent line. So that means that my graph should be above the tangent line. So it should be something like that. But then it means that it is so above the tangent line, that it is local minimum. And similar, if I know that at some point my tangent line is 0, the slope of the tangent line is 0, but second derivative is negative, that means that the graph is below the tangent line. That means it looks something like that. And then that means that it's local maximum. Okay? It's not a proof, but it's very close to the proof, in fact. Okay, and again, how you can remember this. Again, the simplest example that we discussed, y equals x squared. gives you that second derivative is just 2, which is positive, while if you look at the graph of the y equals y squared, y equals x squared, then of course you have local minimum. While if you consider y equals minus x squared, then the second derivative is minus 2, which is negative, and the graph looks like this, and that means that it's local maximum. That's the way how you can remember the second derivative test. Not example, but rather how to remember. Just remember this these basic examples. Okay. Okay. Mm -hmm. Okay, and what I want to say. Yes, so let's now discuss curve sketching. Because now we have all the tools that we need, in fact. Curve sketching. And this will be kind of algorithm. First is to find all critical values and critical points. Maybe you should first find critical points and then critical values, but okay. Critical points. No, critical values are x coordinates, so it's fine. Just the definition. So what does it mean? It means that if suppose you have y equals f of x, and you want to graph it. And so what does it mean? It means that you need to calculate y prime at point x, just the first derivative. Okay, let me do it like that. This is first step. And it says find, calculate y prime. Then find x, okay, find, say, point C, critical values. So again, they are points where first derivative is 0 or first derivative is not defined. Then calculate critical points. So calculate critical points means that calculate the value of your function at these points that you found on the previous step. And this is first step. Second step is test the critical points. So what does it mean? Use, So in some sense, so find local minimum, maximum. And how you can do that? Either you can use the second derivative test, right? Or or if it fails, use the first derivative. Derivative test. So again, what does it mean? It means that if double prime point C is positive, then it's local minimum. If it's negative, then it's local maximum. And in this case, if this is the same as f double prime of point 0 is 0. Okay, third step is from second derivative of x, find the intervals where the function is concave up or down. Concave up, that means that second derivative is positive, and concave down, second derivative is negative. And I forgot to say that first derivative test means that write your zeros on the on the line, x0, x1, zeros, 0 of f prime, and find, say, when the function is increasing, decreasing, and stuff like that. This is the first derivative test. And from the first derivative test, of course, you can determine where the function is has local minimum or maximum. Okay. And yes, and to determine once you determine the intervals where the function is concave up and concave down, from that information you can find the inflection points, right? Because inflection points are, by the definition, are the points where your function changes the concavity. Find the points of inflections. Inflection. Where concavity changes. And fifth step is they're called other in the textbook, and that means that kind of general information, and you can determine from the equation of your curve, such as intercepts, xy intercepts, if they can be found in an easy way. Because sometimes if you try to solve, if you try to find intercepts, you may get some not quadratic, but rather fourth power equation of x, and you cannot solve it. But if you know that it's linear, then why not to try intercepts? So it's easily determined, intercepts. Easily determined. And asymptotes as well. And test for the symmetry. Symmetry, it's kind of general notion, but first of all, you should check if the function is even or odd. Or sometimes you can say something more. Sometimes there is symmetry with respect to a region and stuff like that. But first, the most important is if the function is even or odd. So even means that f of minus x is equal to f of x, and odd means that f of minus x is equal to minus f of x. Draw it. Draw. Basically put all the information that you have on the graph, all your points that you know, all asymptotes that you have, and try to connect in a smooth way. Maybe you can calculate some additional points, but this is basically draw it. Let's start with y equals x to the power 4 plus 4 over 3 x cubed. Okay, so first of all, let's calculate the first derivative. Y prime is equal to 4x cubed plus 4x squared. So y prime is equal, first of all, we see that there is no bad points where this first derivative is not defined, so we only need to find the zeros of my derivative, and that gives me that 4 times x cubed plus x squared is equal to 0, or I can factorize it like that, x squared times x plus 1 divided by 4 first is equal to 0. And that gives me x equals 0 and x equals minus 1. These are my extreme points where probably I have minimum maximum, but we need to check it. And how we are going to check it? Using the second derivative test. So I will calculate the second derivative, which is the derivative of the first one. So it's 4x cubed plus 4x squared. And that gives me 12x squared plus 8x. And y double prime at point 0, unfortunately, gives me 0. So it fails. But y prime at point, say, minus 1 will be 12 times 1 plus 8 times minus 1, which is 4 positive. That means that it's local. So it's positive, so it's local minimum. But nevertheless, I need to use first derivative test. So first derivative test, I need to put it on the line, all my zeros. And so my zeros are 0 and minus 1 and 0. And my first derivative is 4x cubed plus 4x squared. Okay. For simplicity, of course, because I'm interested only in sine, I can calculate the sine of y prime over 4. It will have the same sign as y prime, of course. So I will not get big numbers. And then I will choose test points, say -2, -1/2, and 1. So y prime over 4 at point -2 will be what? Okay, since I have, okay, this is good, but maybe this I don't need it because I need to plug -1/2 and there will be some nice way. Maybe it will confuse you. So y prime at point -2 will be what? 4 times -8 plus 4 times times 2. And so it is -32 plus 16, so it's negative. So that means that here my function is decreasing. Y prime at point -1/2 will be 4 times -1/8 plus 4 times, oh, I put 2. So it should be 4, sorry. I put 2, 4 squared, I mean 2 squared, which is 4. And here will be 1/4. And so that gives me -1, plus, which is, of course, 1/2, which is greater than 0. And the last thing is y prime at point 1. So here I have that my function is increasing. So indeed, -1 is local minimum. And y prime of 1 will be what? Will be 4 plus 4, which is positive. It means that it continue increasing. And so that means that 0 is not local minimum or maximum because the sign of the first derivative wasn't changed. Okay. Okay. Okay, so next what we need to do, it was which step? Third step. Oh, it was second step. We need to calculate critical points. So we need, maybe it was first step even, calculate what is the value of my initial function at the critical points. So point -1. And again, do not confuse it with the derivative. It is our initial function. So our function was y equals x to the power 4 plus 4/3 x cubed. That means that y of -1 will be -1 plus 4/3 times -1. Oh, what I was doing. So it's like that, and thus it will be 1 minus 4/3, which is -1/3. So my critical point is, my first critical point is -1 minus 1/3. Okay, and my second critical point is y at point it's not a critical point, but why not to calculate y of 0, because it's a nice point. We found out that 0 is not local minimum maximum, but still, in this case, it's not easy to, not complicated to calculate what is the value at that point, and in fact it appears to be x and y intercepts, just the origin. Okay, the next step is to calculate, to consider second derivative, and we have calculated that. So y prime, y double prime was what? 12x squared plus 8x. 12x squared plus 8x. And if I factorize it, I will get 4x times 3x plus 3x plus 2. And if I again put my zeros of the second derivative now on the line, it will be 0 and minus 2/3. Zeros of double prime, y double prime. Now again, I should choose test points. Let's say here I can choose -1. Here I can choose -1/2. Okay, for some reason I put it above, but let's put it down. And here I will choose say test point 1. So y double prime at point -1 will be -4 times -3 plus 2, which is positive. Y double prime at point -1/2 will be what? It will be -2 times -3/2 plus 2. This is positive, while this is negative, so the total sign is negative. And y prime at point 1 will be 4 times 3 plus 2, which is of course positive. So that means that here it is positive, then it becomes negative, and then it becomes positive again. That means that that -2/3 and 0 are the inflection points, right? Because at that point, the sign of our second derivative was changed. So it was plus, then minus, and from minus it changed to plus. Okay, okay. Okay. What else we should do? We should again calculate value of our function at that point, value of minus at point -1. We already calculated, I think. Yes. This is our minimum, local minimum. And value of sorry, of -1. I don't need of -1. I need of 0. That's what we calculated is 0, and what I need to find is y of -2/3. Again, if you plug it, you will get -16/81. It's not that interesting, so I'll skip the calculation. Again, you should plug it to the initial function, not to the second derivative. Okay, unfortunately, our function is not even, not odd, and doesn't have any symmetry. So what we can do is, we can find another intercept. So we found that when x equals 0, y equals 0. But what if y equals 0? So one solution we already found, but there is another one. So our function is 4x x to the power 4 plus 4 over 3 x cubed is equal to 0, and I can factorize it like that. X plus 4 over 3 is equal to 0. It gives me that x equals 0, that's what we found already, or x is equal to minus 4 over 3. And that's it. Let's draw the graph. So at 0, I have 0. At point minus 4 over 3, which is somewhere here, this is my another 0. Point minus 1, I have minus 1/3, which is somewhere here. Okay, let's do it here. This is another point. Then I know that at point minus 2/3, which is somewhere here, I have minus 16 over 18, 1, which is here. So here's my point. Okay, and what else I know? I know that on the interval, so my first derivative test, that says that from minus infinity to minus 1, it was decreasing, then it was increasing until 0, and then it starts to continue to increasing. So, and of course, if I look at my function, x to the power 4 plus 4 over 3 x cubed, I see that if x goes to plus infinity, my y is also goes to plus infinity. And when x goes to minus infinity, the leading term, which is x to the power 4, will kill. So I have something very big positive and something which is negative. But x to the power 4 will be greater than x to the power 3, of course. So still on minus infinity, y will go to plus infinity. Again, you can show it, say, plug in x to the power 4, and then you'll have 1 plus 4 over 3 x. So at both infinities goes to 0, 4 over 3x like that. This goes to 0, and so the behavior depends on the leading term x to the power 4. So I have somewhere here, my function will go to plus infinity, and here it will go to plus infinity as well. And from minus infinity to minus 1, it is decreasing. And also I know that my concave is up until minus 2/3. So that means that I can connect it like that. Then at point minus 2/3, my concavity was changed. You see that it becomes concave down until 0. That means that now I need connect not like that, but like this. And then at point 0, it changes again to concave up, and my function still increasing. So it goes like that. And this is the sketch of the curve. Example 5, I will not do all steps, but I will emphasize some features. So suppose I have x minus 2 to the power 2/3, then y prime, if you calculate it using generalized power rule, for example, or chain rule, 2 over 3 x minus 2 to the power 1/3. And if you continue and calculate second derivative, it will be minus 2 over 9 x minus 2 4/3. And so what is crucial? The crucial is that now at point x equals 2, your function is defined, while y prime is not, and y and first derivative is, and second derivative is not defined. And so at this point, again, it can be local minimum maximum, and also, as we discussed, it can be the inflection point as well, because at this point neither first derivative or second derivative are not defined. In fact, if you do all the steps, first derivative test, second derivative test, and determine the point that it's local minimum maximum and plot the graph, in fact, you will get a graph like this. We also have seen that before. And again, because you see that function is not very smooth at the origin. And that's why y prime and y double prime is not defined, but this 0 is local minimum and also, but not the inflection point, right? Because here is concave up. Sorry, it's what is it? It is concave down. Sorry, yes, concave down, and here is still concave down. So x equals 0 is not inflection point, but it's a local minimum. So this example shows you that even second derivative at this point is not defined, so it could be a inflection point, but no. Second derivative is not defined to 0, gives you the points where you can have inflection point, but not necessarily have. And another thing, it's a slightly generalized example. Example number 4, where y is equal to x. Instead of this, what is given in the textbook, let's put it here, square root on the top. Then this is about the last step, the almost last step, number 5 step, I think. Fifth step, about the asymptotes. If you calculate the limit, first of all, this function is defined for x greater than or equal than 1, so you have limit when x goes to infinity. And the limit of such expression, how to find it? Again, you can play with the function and write it, divide by square root of x, both numerator and denominator, and you'll get something like this. And so 1 over x goes to 0, and the limit is 1. And what does it say? It says that when x goes to infinity, so in previous examples we have, even in this example, we have plus infinity, and this is plus infinity. But in this case, your function will go to 1. So this x equals 1, or y equals 1, sorry. And your function will go to the 1, and in fact, it will go to the 1 from the above. So it will go like that. This is one thing about asymptote. Another thing about asymptote is given in the example y equals x squared plus 16 over x squared. Again, if you calculate the limit, the limit y of x when x goes to infinity, it is the limit of x squared plus 16 over x squared when x goes to infinity, and that will be, of course, infinity, but instead of that, you can say that what is called dominant term. the term which is much bigger than another. Of course, 16 over x squared will be very small comparing to x squared when x goes to infinity. So in some sense, at the infinity, your function will behave like x squared. And also, of course, you have vertical asymptote because you have problem with the denominator here, plus vertical asymptote, x equals 0. And what you will get some function. If you look at the textbook, it will look like, or you can repeat all steps that we discussed. And in fact, you see that this function is even, x to minus x doesn't change the function. So it's even function. So it's symmetric with respect to y-axis. But what is important that if you graph y equals x squared, the observation above says that at infinity, your function will be very close to your parabola. So this curve will be very close for the parabola from both sides, of course. It will be close here and it will be close here as well. This is sometimes called asymptotic curve.